His performance is about to begin. This is Serafim Kalliadasis, speaking on the moving contact line problem.
Thank you, Darren. Okay. First, just a warning from me. I think I have more material than the time that is allowed me, and I think I probably go over the after 4:30 for a few minutes. I don't know how many yet. I don't know exactly. So I figured since it's the last talk of the day, you wouldn't mind sticking around. On the other hand, it has been a long day, and if you want to go, then you are welcome to go. The second point is I was in Vancouver yesterday, and therefore I'm somewhat disoriented. So if I say things which don't sound right, it might have something to do with this. Okay, so this is work by recent progress. Ah, yes, good point. Yes, absolutely. Yes, I forgot all about it. If I can find it. Yes, it's on. Switch on. I couldn't see the light. There, green. Okay, thank you. Thanks, Uwe. So this is work, but done together with a number of people. We have Andreas Nold, an amazing PhD student in our group. By recent progress here, I mean progress primarily in our own group at Imperial, but also I will be highlighting some of what we think are key works on the problem over the years. So we have Andres, an amazing PhD student, former postdoc Antonio Pereira. He's currently faculty at Nancy in France. Postdocs Ben Goddard, David Simply, Mark Pradas, and Marcus Schmuck. Former postdoc Nico Sava, who is a lecturer in mathematics at Cardiff University, okay? And PhD students Peter and Raj. So over the years, our work has been funded. Sorry?
Schmuck is definitely not Israeli, right?
In fact, it's Swiss.
That
And
would be a funny name.
I think it means jewel. Yes. And so our work has been financed, supported, if you like, by Multiflow. That was the large EU network that, in fact, was coordinated by this person here. And he's telling me that it's less work. It was less work than this program. Of course, the engineering and physical sciences is cancelled via a platform grant, and more recently by an advanced grant from the European Research Council, which aims to develop methodologies for dimension reduction of multi-scale physical systems. So this is a particular case, if you like, of such systems. An outline, I will start. Part of the reason why this talk is a bit longer is because I decided to add some pedagogical information at the beginning. So an introduction to the problem. We're going to revisit the Moffat analysis to see if we can actually give some additional insight on this problem. We're going to look at the problem within the thin film equations framework, because all the equations, Navier-Stokes and so on, are simplified substantially. Within this framework, we are going to analyze a number of problems, a number of models that are used to remove the discontinuity associated with the contact line, slip models, precursor field models, a complex model, the interface formation model, and we will do that for heterogeneities, chemical and topographical, and we're going to compare the different models. And more recently, we're going to look at, this is more recent work on diffuse interface methods. In particular, DFT here is short for diffuse interface, density functional theory, in particular, density functional theory, yes, DFT, phenomena associated with confinement, and also some information on dynamic density functional theory. And then we will conclude. So obviously there are many applications. For example, this is a case of oil water, okay, where a saturated rock is saturated with oil. Well, shown here, the water is actually used to push oil out of this structure. And this is an idealized rock surface. It's a smooth planar substrate. We have an oil-water interface here. In various biological settings, okay, insects working on water or on the surfaces of wet plant leaves, and in technological applications from inkjet printing to the deep coating problem, where typically you have a fiber or a plate which is actually withdrawn out of a pool or bath or liquid. This is effectively the Landau-Levitz problem. So let me try to define now the moving contact line problem. A lot of us are familiar, so I'm just reviewing some of this work. We have a liquid-gas interface that moves from the left to the right with velocity u. And if we introduce a frame of reference that moves with the interface, okay, moving frame of reference, then the wall appears to be moving from right to the left. Theta sub c here is a macroscopic contact angle. This is the actual angle that this interface forms with the substrate, and this intersection between the interface and the substrate is what is known as the contact line. So it's not difficult to see that right at this point is part of the interface, so it's got to be stationary in the moving frame, and at the same time it has to satisfy the no-slip condition. It's not difficult to see that this gives a multi-valued velocity, and therefore formulating this problem classically in the usual hydrodynamic formalism, if you like, with no slip, you do not expect a solution. The first, if you like, person to highlight these difficulties is Moffat in an old paper that we will see soon. Moffat looked at the case of a wedge, a fluid void wedge, and then we have the seminal work by Hugh and Scriven in 71, where they looked at a fluid wedge, the same wedge problem, but a fluid wedge. Moreover, Hugh and Scriven showed that if you were to introduce a polar coordinate system centered at the contact line, where r is a radial velocity, is a radial distance from the contact point, then with respect to this distance, you have a singularity for the stress and the pressure. Okay, so you have a 1 over r discontinuity for the pressure and the stress in the classical formulation. Let's see why I cannot do the, oh yeah. I had some overlays here. Any idea why they do not, where is the technical guy? I had some overlay here. Any idea why? No? Sorry? I had an overlay here, but it doesn't show. It doesn't matter. It's okay. That's fine. Let's go to the Moffat problem first. Okay. This is the original paper by Moffat. In fact, this is a long paper that has to do with resistive eddies in the Stokes approximation, resistive eddies in the sharp corner, and in the Stokes approximation. Okay. So the contact line problem, the fluid void wedge, the contact line problem, is actually just about a page in this rather long paper. This is the Hugh and Scriven paper that I mentioned earlier in 1971, where they looked at the fluid wedge. Okay, so let's start with revisiting Moffat analysis. So this is already dimensionless equations. This is continuity. This is the momentum equation without the unsteady term. Okay, we're in the moving frame. Here we have the total stress tensor. Okay, P is the pressure, D is the rate of strain tensor. That's a Reynolds number. If you have a length scale and a velocity, you have a Reynolds number, and then you can introduce the stream function u. ER and E theta are unit vectors in the r and theta directions respectively. So we have a polar coordinate system, and the velocities u and v in these directions are given here in terms of the stream function. One then can stipulate this power law dependence as you approach the contact line, where gamma is an exponent yet to be determined and is positive. And it's not difficult to see if you substitute this stream function here, this dependence, into the equations, you get the following order of magnitude estimates shown here by balancing appropriate terms. This is an easy exercise to do. In particular, what one sees here is that the inertia terms in the left-hand side of the momentum equation are negligible for small r and gamma positive. Therefore, we can neglect these terms here, and we are in the Stokes regime. So we are in the Stokes, or so-called creeping flow regime, and then in this case, the pressure gradient is simply balanced by the viscous forces. Remember, T is the total stress tensor, and you can write the viscous forces in this form. Okay, this is sort of pedagogical. So from the Stokes equation shown here, you can use the stream function that we had before, written here in terms of the velocity. So the velocity field is the cross product between the grad operator and this vector here, where k is the unit vector in the z direction, okay, with respect to a Cartesian coordinate system x, y, and z. This is z. Last week in Vancouver, a lot of people kept on saying z. I learned this as z, but let me know if you disagree. And then by taking now the curl of both sides and using vector calculus, again, this is a nice little exercise for students. It's not difficult to see that you get a biharmonic equation for the stream function. And this operator here is effectively the Laplacian operating on itself. So this is the Laplacian in polar coordinates. It's also useful to have the pressure gradients here with respect to this polar coordinate system, and also the shear stress components. Okay, this is nice vector calculus exercise. Take now, because this is a linear, effectively the biharmonic is a linear PD. We're all used to separation of variables for this type of equations, let's say. And now assume this separable form, this separable function, r to the gamma that we had some function of theta, and substitute it into the biharmonic, and you get this fourth order OD for f naught. Now, if you didn't have this f naught here, okay, you can solve this with, let's say, something like the method of characteristics, or there is a transformation that converts this to a second order ODE. If you didn't have this f naught, the transformation would simply be f naught double prime equals, let's say, some other function g. From this, now again, for the students in the audience, you might want to see what the transformation would be in the presence of f naught. So this is converted to a second order ODE. It's a nice exercise. And you can solve this in particular. What you find here is this general solution that has 4 integration constants, C1, C2, C3, C4. These are arbitrary constants, which then means we need 4 boundary conditions to determine them. But also what you note from this solution is that this particular value, 0, 1, and 2, give you the general solution. For example, gamma equals, let's say, 0, kills this sine theta term. So you go from 4 constants to 3, right? If gamma equals 1, this becomes minus sine gamma theta, and this becomes sine gamma theta. So you combine C1 and C3, right, into one constant, and you can rename this constant. So again, you drop the number of constants from 4 to 3. You reduce this. Hence, this degeneracy. In particular, this is just effectively an eigenvalue problem, and you can solve this eigenvalue problem and find these values 0, 1, and 2. But here is the general solution. Again, a nice exercise to do that for the 3 degenerate values, gamma equals 0, 1, and 2, where the different constants A1, A2, A3, and so on are written here in terms of the original constants C1, C2, C3, and C4. All right. Remember, we need 4 boundary conditions. What are those? First of all, let's start with the kinematic conditions. Vanishing normal components at theta equals 0, which is effectively the location of the interface in the moving frame, and theta equals theta sub c, theta equals 0 is the wall, theta equals theta sub c is the interface. So no penetration velocity on the wall and on the interface. We have the tangential stress balance on the interface, and notice here that we have included the gradient of the surface tension in case that there are Marangoni effects due to thermocapillarity, let's say temperature variation or chemical composition, i.e. surfactants. So this is the more general term of the tangential stress balance. This sigma now is the total stress pressure, total stress tensor, yes, that includes the pressure here. But if we forget about the Marangoni effect for a second, okay, then the tangential stress balance reduces to this simple expression on theta equals theta c. So we have 1, 2, 3. We need a 4 condition. Of course, if we wanted to solve this problem properly, if you like, we would have to determine the shape of the interface as we approach the contact line. Why is that? Because there might be something like viscous bending there, in particular for sufficiently large capillary numbers. The capillary number here is a kind of a standard dimensionless parameter. It compares viscous forces to surface tension forces, okay? So this is effectively viscous forces, mu is viscosity, sigma is surface tension. So if this number is sufficiently large, then this viscous bending would be important, and then we would have to solve for the shape of the interface. But here we follow Hewen, Scriven, and Moffat, and we take the interface to be simply a planar surface, just a wedge coming down to the contact line. Okay, so for closure we need an extra condition, okay, and we can either go with no slip, or one of the most popular ways of removing the discontinuity is the so-called slip boundary condition, okay, which is discussed here. If we have no slip, then it will give back the moving contact line problem. This is the Navier slip condition that was proposed by Navier in the 1800s. All this is saying is that the tangential velocity on the wall is proportional to the shear stress there. Sigma we defined before, the stress tensor, where lambda here, this proportionality coefficient having units of length, and this is a slip length. So this is the boundary condition for no slip. That's the Navier slip that we have seen here. This is the shear stress. There are 2 interesting slip models, an inverse linear slip and an inverse quadratic slip shown here, where the effective, if you like, slip coefficient is inversely proportional to the thickness, the distance between the interface h, if you like, and the wall. Okay, in polar coordinates, this is given as r sine theta c. This theta c is the macroscopic contact angle. By the way, this theta c is sometimes taken to be stationary, sometimes taken to be dynamic. We will see this, yes? Why these 2 are interesting? They're interesting because they can actually, if you like, regularize the pressure discontinuity completely. With a simple Navier slip model, as we will see at the moment, the pressure, in fact, has a logarithmic singularity, where here these 2 models regularize it, okay? All right, so we have sufficient number of boundary conditions. These are 4th boundary condition. Let us substitute there the r to the gamma times f naught of theta separable function that we had. So this is the no-sleep condition shown here in terms of R and F node. That's the Navier sleep, this is the inverse linear sleep, and this is the inverse quadratic sleep, all right? And then obviously this first one is satisfied for gamma equals 1, which gives you psi equals R F naught of theta. Now here gamma equals 1 does not work because although you balance the wall velocity to the bulk fluid velocity at the contact point, with gamma equals 1 you get that these terms dominate. These are the shear stresses and there is nothing to balance them. So it's not a good balance. So in fact you get dominant balance here when gamma equals 2, gamma equals 3, gamma equals 4, and then the tangential velocity of the fluid, the bulk fluid tangential velocity on the wall becomes a higher order term. Yes?
So when you have the H and you have the inverse linear slip, do you give a boundary condition at H to match
The
with
boundary condition, in fact, this is a good question. The boundary condition for sleep is throughout the wall. It's everywhere, so the fluid sleeps everywhere. In computation, CFT type computation shown, what people do for convenience is they do it on a grid, they put some sleep that exponentially increases as you approach the contact line, and exponentially away from the contact line you get the no-sleep boundary condition. But here it's everywhere. Is that? Yeah. So for the different values here, gamma 1, 2, and 3, 4, this is the corresponding stream function. What you can do once you have the stream function, well, you can get the velocity fields. That's the stream function what you have no sleep. This is U and V, the velocity fields. Notice here the shear stress and the pressure as U and Scriven obtained, okay, 1 over R singularity, 1 over R. Moreover, what you can do, okay, this function QC here depends on your theta C. What you can do also is obtain the velocity here at, this is your velocity here, on the interface, theta equals theta sub c. Remember, because of our polar coordinate system, the interface theta equals theta sub c. And you get this expression for the velocity. So you have minus u times this quantity in the brackets, and it turns out this quantity in the brackets is always positive. So the fluid velocity is minus u times a positive velocity on the interface, a positive term. So what this means that everywhere in the bulk fluid, as the fluid, and not just on the wall, as the fluid approaches the interface, it's going to accelerate from a finite velocity. It's going to have an infinite acceleration to move from one value of the velocity, which is u, to another value, which is minus u. Okay, so this is everywhere in the bulk as you approach the interface. Another interesting observation is that if you take the contact line as 180 degrees, because of this sine theta c dependence, okay, the sine of 180 is 0, you get 0 shear stress and 0 pressure on the wall. So you have regularized in the particular case where the contact line, the contact angle is 180 degrees. So in this case, if we can draw the interface, it will look like that, a bit like a caterpillar, if you like. Yes. So let's say this is your liquid, this is your gas, but the contact angle is now 180 degrees, and this regularizes completely the discontinuities of the contact line. This is a particular case beyond to what we will be discussing here. It was first highlighted by Ben and Timpson. Later on, Len Pisman and Nir did a study on this. Then we have Gan and Dusan, and more recently Benilov and Viniki revisited this problem. Let us look now at the Navier sleep. Okay, this is a popular model to remove the discontinuity. Stream function velocities, that's a shear stress. Regular. Look at the pressure. The pressure is better in the sense that the singularity is weak. It's a logarithmic singularity. It means that it is integrable. It means you can get an overall finite force at the contact line. Okay. Nevertheless, still one should worry about the fact that you have a singularity in the pressure, albeit weak. After all, we're dealing with a liquid here, yes? And if the pressure in the liquid tends to, let's say, minus infinity, you might have evaporation effects and so on, cavitation, etc. These are the cases for the different sleeps. Okay, so for the students, because this is videotaped, it would be good to go through this exercise. Different parameters here, right? N equals 1 is the inverse linear sleep, and N equals 2 the inverse quadratic sleep. What we are interested in is the tau r theta here, okay, which you can see is actually perfectly regularized, and the pressure also perfectly regularized. Still, as we will try to discuss later, not quite satisfactory. These models are not quite satisfactory because they're missing something. Thin film framework. Why thin film? As I said before, you simplify the overall equations. Governing equations, again for the students, these are dimensional variables with the overbar here, dimensional variables, so this is the usual suspects. Let's say incompressible continuity, momentum equations, no penetration condition on the solid boundary, tangential stress, okay, sigma bar again here is the overall stress, That's your slip coefficient. I didn't mention that these are unit vectors. Yes, this is tangential and normal to the wall. So this is Navier slip. And what we have on the interface is, of course, a kinematic condition. So F bar equals 0 is the interface, tangential stress, and normal stress balance. The first step one needs to do, again with simple vector calculus, convert the boundary conditions to Cartesian form, and then convert these equations here to Cartesian form. Okay, so these are the sorry? Yes, so that's the Cartesian form. The kinematic condition, the tangential, and the normal stress condition on the interface. We have written this in terms of this curly h, yes, function, which is effectively the axial curvature. It's a measure of the axial curvature. What one then does in the thin film approximation, it introduces a small parameter epsilon, which is the ratio of the vertical over the horizontal scale in the system. You can see this epsilon, this h bar here over x bar is epsilon exactly, yes, assuming that h over x, the slope is order 1 in the new coordinate system. And these are all the parameters, all the terms here multiplied by various powers of epsilon here, highlighted with epsilon in red. That's the Reynolds number there. This is the no penetration, that's the slip boundary condition, and then this is the kinematic boundary condition, the tangential, and the normal stress balance. Typically, the capillary number that we wrote there is of order of epsilon to the power 3. Governing equations now, there are 8 of them. It is not difficult to see that you can solve them sequentially, so to speak. Starting, for instance, with 3. The pressure is not a function of z, so therefore you can integrate 2 straightforwardly to get this second order polynomial. And then it goes like you apply the boundary conditions and so on. You find that u is effectively a semi-parabolic velocity profile. From continuity, you can get v, substituting everything into this expression, which is the kinematic boundary condition, an equation for h. This is the thin film equation where lambda, the simple Navier slip model. Yeah? So there we go. Let us see why we do not have a solution of the classical problem. That is, when you satisfy the no slip boundary condition, you try to satisfy in a thin film framework. The testbed case here, the classical testbed problem, the model system is that of a two-dimensional droplet that I have actually drawn here. Okay. So with respect to the z-axis, the droplet sits on the along the x-plane, and with respect to the z-axis, the droplet is symmetric, and it's got radii minus a plus a. Okay, minus a plus a, that's the domain. So it turns out that the analysis can be simplified by this coordinate system, okay, which maps the moving domain minus a to minus 1, 1. And again, for the students, this is a chain rule to actually go from one coordinate system to the other. These are all simple things, but when you sit down to do them, you find out that there are some small things that you need to remember. That's the new equation, okay, in this moving frame. That's the contact angle condition, written here in terms of the new coordinate y. Now, typically in these problems, we have quasi-static spreading. That is, spreading in which the film thickness depends adiabatically, if you like, or it depends on time, through the dependence of the radius a on time. So this is an expansion that does just that. And then it's not difficult to see that even by the leading order term h naught of this expansion, you do not satisfy the boundary condition at the contact point unless you are at equilibrium. Take h naught, that's the slope, okay, evaluate this slope at the contact point, I substitute it here, and you get this expression for the radius. And this expression is precisely the equilibrium value because of the non-dimensionalization that we have actually used. Not surprising, there have been many different models to remove the discontinuity, and I'm going to discuss some of them here. That's the Navier slip model. So this is the thin film approximation with Navier. The inverse linear slip is in a work by Rukenstein and Dunn. This is the inverse quadratic slip, a nice paper by Helen Mixes. Here in this overlay, you have different slip scenarios: no slip, partial, perfect slip. In a perfect slip situation, the bulk velocity comes all the way down to the substrate with the same value. Okay. More models. This comes back to the Fromkin and Deriagin school of thought in Russia. The precursor film models, in which you have a disjoining pressure term here, which actually induces this energetically stable precursor film of thickness h star at the front of the apparent contact line. And effectively, it's not difficult to see how you can get this. By integrating the disjoining pressure, let's say between h star and some value h here, you get something like, which is known the disjoining energy. And you can minimize this disjoining energy right at the precursor film thickness. And there are different models. One is the van der Waals model by Schwartz and Nelly. You have this term here, which denotes long-range attractive intermolecular interactions, and this is a short-range repulsion. The Sharma model here, which has a short-range repulsive term which is exponential, where the parameter d here controls the decay of this exponential. This is a model suggested by Pisman and Pomot. The interface here has a thickness epsilon. We're going to come back to this model soon. And they actually imposed a density here on the wall, which is different to that in the bulk. This induces a density gradient, and there is an associated effective disjoining pressure given here, where W here is a parameter that controls the wetting characteristics. Okay. Another models was suggested recently by Alex Rednikov and Pierre Collinet in Brussels. The basic idea of this model is under usual conditions, more or less to one extent or another, all liquids are volatile, and this volatility should have an effect on contact line motion. This is an evaporative flux. This is the wall superheat. It's the difference between the wall temperature and the saturation temperature. And this is a term that is known as the Kelvin effect. The Kelvin effect is telling you how the saturation temperature of a curved interface, how the saturation temperature of a liquid-gas interface is affected by curvature. If you have a flat interface, you have a certain saturation temperature given the ambient pressure. Remember thermodynamics. If you curve it, then the saturation temperature changes, and this change is proportional to the curvature which is given here in the long wave approximation. Okay. Another interesting scenario here in the nonlinearity journal by these authors. Now the discontinuity is removed via shear thinning. That's an interesting scenario. The basic concept here is that although the shear stress tends to infinity at the contact line, the viscosity, precisely because of shear thinning, tends to 0, and then you remove the discontinuity. Alpha, larger than 1 is shear thinning, smaller than 1 shear thickening. Tau tilde here is the stress at which the viscosity drops by half. Now, this is all the models, popular models in the literature which you can find. So here we go to one of the most complicated problems that has been suggested for this phenomena, the so-called interface formation model suggested by Yuli Sigmusaif in 1993. Yuli referred to this phenomena, Yuli thought of the contact line problem as part of the generic class of interface formation phenomena in which an interface appears or disappears. For example, if you have, let's say, droplet coalescence, the interface, you lose interface, so interface disappears. If you break up a droplet, the interface appears. There is a more recent version to this, and he was clever here. There is a reason which I'm going to try to explain, to include mass transfer between what we call the surface layers and the bulk liquid. I will come to surface layers shortly. A gray area here, yes, I will try to highlight it, if provided you don't kick me out of the room, by Bedoin Billingham. Interesting questions here. Not surprisingly, this has generated an amount of debate and questions, both for the formulation and the physical basis of the model. Some of them are here. There was recently, for example, a couple of years ago, a special issue of this journal, European Physical Journal Special Topics, that was edited by our friend and collaborator, Manuel Velard in Madrid, where various people entered the debate. Len Pisman, Uwe Thiele entered the debate. Of course, Yuli had to enter the debate, and so on. We had a paper there, but we didn't enter the debate. But nevertheless, in 2012, in this Physics of Fluids paper, we critically examined the model. So let me give you now the essence of this. First ingredient. You have the surface layers in the immediate vicinity of the liquid gas and liquid solid interfaces, where the density is different to that in the bulk. Okay? Although these layers are effectively have 0 thickness because they are taken in a continuum approximation, they still allow for different boundary conditions on either side. Okay? For example, you can have a slip boundary condition between the bulk and this solid surface layer, and a no-slip condition here between this solid surface flow and the substrate. But this, in some sense, is never done explicitly because this thickness is the thickness is 0 effectively, and in some sense the properties are average across the thickness. I will show you how this is done. This cartoon here starts to remind you of the concept of surface tension. Okay, so if you have a liquid molecule here in the bulk, it's surrounded happily by neighbors of the same liquid. If you move to the interface, then you have, of course, a smaller number of liquid neighbors because you are exposed to the gas. And this shortfall, if you like, in the neighbors, the shortfall in energy manifests itself as interfacial energy or surface tension. That's just to remind you. Second ingredient. This is a crucial ingredient of the model, as I will show you. Yes, without this, the model degenerates to an obvious slip model. As these molecules, let's say here, on this liquid gas surface layer, experience surface tension sigma on 2, they have to move towards the contact line. Then they have to move away from the contact line to experience equilibrium sufficiently far with the surface tension sigma 1s. Some rearrangement has to occur during this process, and this rearrangement has a finite time scale tau. So this is a surface tension relaxation time scale. And that is Young's equation. Yes?
Can you say a few more words about the shear thinning model?
The shear thinning, yes, what about it? What?
I didn't quite understand how that works out.
So the basic idea is, although the contact line, the shear stress tends to infinity, yes, because we have the singularity, but at the same time, as you approach the contact line, the viscosity tends to 0 because of the shear thinning.
And the shear rate
So it tends, it's finite, they have shown in the paper.
No. The shear stress goes to infinity. The viscosity goes to 0. So the shear rate has to be infinity squared.
That's another complexity, but the model can be used to regularize the pressure and that's from the paper. That's from the paper, the pressure and the, yes. All right, let me show you now the conditions here, yes? So we have the bulk condition, the bulk equations. This is continuity, that's Navier-Stokes. This is a busy slide, but we have to go through the equations. This is the normal stress balance. That's the gas surface layer surface tension, Mg is a normal vector to this surface pointing towards the liquid. This is a shear stress. This is the gradient here of the gas surface tension. Now, so that's a shear stress balance. This is an equation that actually denotes mass transfer between the bulk and the surface layer. So here m is an indicator function. If Hm vanishes, you don't have communication in terms of mass transfer between the two. Hm is unity is for the more recent formulation of the problem. Kinematic condition, this is an equation here that tells you about conservation of mass here, okay, in this layer. This GE here denotes effectively, rho G denotes the equilibrium gas density of this surface layer. That is communication in terms of the bulk tangential velocity. This subscript here denotes tangential velocity, and this is the tangential velocity of the gas surface layer. Alpha is kind of a Darcy law parameter, and this constitutive law here links the surface tension here to the density here. Rho S0G is some reference value with respect to which the surface tension vanishes. It's just a law here, a constitutive law. Gamma is inverse compressibility. Okay, we go here. Similar equations, right? This is the indicator function, okay? We said before, this is communication in terms of mass transfer between bulk and solid surface layer. We have the conservation of mass. This is our constitutive equation of penetration. Let us look at this. If, for the moment, the shear stress, and this is the tangential bulk velocity. Remember I said that these two vertical bars as a subscript indicate tangential velocity. If you forget for the moment this term, all this is telling you is right on this boundary, the tangential stress is proportional to this beta times this velocity. This velocity is effectively the average between the bulk liquid velocity, the tangential bulk liquid velocity here, and the no-slip here, and that is how the no-slip boundary condition is satisfied. They satisfy on average with a layer of 0 thickness, right? So beta is called a sliding friction coefficient, but effectively is a slip coefficient, and it has units of 1 over length. At the contact line, we have conservation of mass shown here. This is the Young equation assumed to be valid away from equilibrium. And then here we come to John Billingham, who actually tried to solve the problem for a wedge, like Moffat and Hewen-Scriven did, and he found that there is a missing boundary condition. He communicated this to Bedeau. Bedeau wrote a nice paper in '76 with Albano and Mazur on the thermodynamics of immiscible interfaces, and in fact, Yuli's model is effectively continuation of Bedeau's work. And Bedeau says, but of course, there is a missing condition. Here it is. So via some entropy arguments in which the contact line is considered a thermodynamic entity, equipped with things like line tension. Later on, this was contested by Yuli because as we are in the continuum limit here, there is no such thing as line tension. So there are, as I said, a lot of debates there. He was able, Bedeau via the energy conservation, to actually obtain this condition shown here, where this U naught and UG naught are effectively, they have units of velocity, and they're taken to be equal, and for simplicity, in which what one says effectively is that the energy production right at this point is effectively balanced by difference in chemical potentials. There's no chemical potential there because there are some arguments close to equilibrium to represent via Taylor expansion the density differences in terms, but the chemical potential difference in terms of these densities. Yes.
Could you say again how do you choose the width of this special region?
It's 0.
There, the surface?
It's 0. It is there, but it is 0.
Fine.
Yes? This is, so forget this term. Look at this. So this here is the tangential bulk fluid velocity, and this is actually, the quantities are averaged effectively across 0 thickness layer, because we have the tangential plus 0, and the average of the two is this. Yes?
So those are really jump conditions across some sort
So
of...
in a way you have this condition
Okay.
here. Yes? It's a sliding friction condition. Okay? But although this is 0 thickness, you have these different parameters which come into the problem. All these quantities of these different thickness, like the densities and the surface tension. Yes? Sorry? Yeah, this is the model.
Right afterwards.
What's that?
Maybe you can explain it to me afterwards.
Afterwards, yeah, we can discuss this about this for a long time. But let's look at this on the testbed problem that we discussed earlier. This of a two-dimensional droplet. This is a problem that was done by Hawking for the Navier slip model. We revisited with Nikos a few years ago. Okay, so the contact line velocity here, you can see you get the velocity in terms of the surface layers velocities. The conservation of mass involves the densities, equilibrium densities in the layers. The long wave approximation here, epsilon is effectively a measure of this macroscopic contact angle here. There are about 10 parameters in the problem. This is the dimensional sliding friction coefficient. This is a parameter that takes into account the mass transport effects between the bulk and the surface layers. That's the Darcy type parameter times beta. Okay, that's the dimensional surface tension relaxation. And this lambda always appears as a ratio between a capillary number and lambda. This is the ratio of the two equilibrium densities for the surface layers. So what we are going to do now is look what the long wave equations look like here. Okay, you have these two terms, the usual long wave equation, but we have two additional functions A and B. These are proportional to the shear stress and also the velocity on the wall. And these two equations are satisfied by A and B. And we're going to view this in the framework, if you like, of mass asymptotics, where we have an inner region close to the contact line with functions psi, A hat, B hat of order 1 over B beta bar. So beta bar is large. And then an outer region where this is not important. The most important parameters, although this problem has several parameters, the most important parameters, I would say, are beta bar and tau bar.
Have you started talking about dynamic contact lines?
Not yet. I hope I can finish.
Because you talked about velocities. Of the
Yes.
We meant velocity at the contact line.
I meant the A dA dt. This is the velocity of the contact line. That's the contact line velocity, and there is also the bulk velocity of the fluid at the contact line.
Yes.
The two could be different. Yes. This is kind of subtle point. Notice the dimensionless relaxation surface time scale, surface tension time scale is at the right hand side of this equation. So if you switch it off, you have these two simple equations to solve for A and B. And if you solve that, you get back the Navier slip model, where the Navier slip coefficient is the inverse sliding friction coefficient. So this model degenerates to Navier slip if you switch off the relaxation of surface tension. Yes, so this is the main point. So we go back here with the full equations. The contact line conditions, that's conservation of mass, Young equation, and this is the additional condition by Billingham and Bedeau. Curly D here is a function that is given here. Okay. Something about the outer solution as you approach the contact point. This is the behavior, this can be done, and you get this typical logarithmic behavior. The inner region is actually complicated, and you cannot solve it analytically. It can only be done numerically, but you can get analytically the asymptotic behavior as you approach the bulk, okay, the outer region, provided you have satisfied the conditions at the contact line. Okay. Right, so this is the behavior of the inner, and this is the behavior of the outer as we escape the contact line. As in the case that Hawking looked at, the logarithmic terms do not directly match, but still you can do matching if you take the third powers of the slope and the negative third powers of A and B, and you get this expression here for the rate of spreading. C naught is not determined yet, but we can still see the effect of C naught on the radius A of t as a function of time. So increasing C naught actually delays spreading. To determine C naught, one has to do it's quite a delicate analysis of the inner region to obtain C naught. And it is obtained in some sense in a self-consistent fashion, but one can then say in terms of the different parameters, but then one can then argue, but okay, do we know these remaining parameters? Do you see what I mean? If we don't know C naught. So it turns out that you can write all the inner regions as a system of seventh order system of two ODEs, so it's a seventh order system. And these are the pertinent behaviors here at infinity. And you need to suppress behaviors which actually are unbounded, okay, at infinity, and therefore you will not be able to match to the outer region. And there are three of them, two exponential behaviors which are unbounded and we have killed, and one algebraic which we have also killed. This algebraic we know, we want. So 7 minus 3 unwanted behavior means 4 degree of freedoms, yes? And these are the 4 degree of freedoms, these 4 constants here. In the inner region, on the other hand, we have the 0 height, okay? And it means 7 minus 1, 7 degrees of freedom here, okay? So on here, so one condition from here and 3, 4 conditions from 7 means 3, okay? So we need 3 additional conditions, and these are the following. Mass balance through the contact line, the Young equation, and then we have the choice. We can either choose Bedoin-Billingham additional condition, remember due to the energy conservation at the contact line. Unfortunately, this one will give us an infinite pressure at the contact line, the pressure with logarithmic singularity. So we could impose that the pressure is regularized there, okay, by having effectively this, killing this degree of freedom here, so killing the logarithmic behavior, and having a more acceptable solution. Still problematic, as I will try to emphasize. So what is interesting is that although they thought there is a missing boundary condition, imposing this condition gives you an infinite pressure, with a weak singularity, of course, and you cannot impose regular pressure plus Bedoin-Billingham. The system is overdetermined because you just need 3 conditions. All right? So this is another, that's why I mentioned to you some kind of a gray area here. This is the influence of the different parameters on this constancy node. In these two graphs, we don't have the mass transport effects between the bulk and the surface layers. Here we do, okay, so this is the effect, if you like, here we have it, here we don't have it, but here we don't have it, and we also have the Bedoin-Billingham condition. The bottom line is that C naught is some parameter which varies, let's say, I don't know, between minus 20 and let's say 60 or something like that. Now here is what happens to the topology of the flow field in the vicinity of the contact line. In this left graph, we do not have mass transport effects, okay? So we have effectively this kind of topology, this kind of streamlines. But when we have the, if we include, if you like, the mass transport effects, then we get this additional return flow here. This is kind of a flow induced by a Marangoni-like effect, but associated with surface tension relaxation, not thermocapillary or chemical variability. We are now in a position to compare two sleep models. Often in the literature, sleep models are applied with a dynamic angle which is equal to the static one. Now, the interface formation model, it turns out, has a velocity-dependent contact angle, so we could correct the sleep model with this perturbation here. And then going through the asymptotics, what we get here, this expression, which is similar to that of the interface formation model, where the constant now C naught is replaced by this constant C and S, okay? And if you do the Rubinstein and Dunn inverse sleep model, what you see there, this is the case for an obvious sleep, so we have the logarithmic singularity, but for the Rubinstein and Dunn, we have a regularized pressure. Okay, remember that's why I told you we have this 1/h dependence. But unfortunately, all sleep models and the original interface formation model will give you that the bulk fluid velocity at the contact line equals to the contact line speed. This means that in the moving frame, the contact line is effectively a stagnation point, and this is shown here. Okay, so a fluid particle on the interface will terminate here. On the other hand, if you include mass transfer, and this was the indicator function, then you can see that you have now a perturbation to the contact line speed, this one, which relaxes the stagnation point and therefore allows you for rolling motion. Okay, so it allows you for rolling motion. You can see physically why, because if you have mass transport, the fluid enters the surface layers, comes into the contact line, and then exits. Okay, that was really why these effects were considered. And this is again what C naught, remember I told you, has typically values, I don't know, minus 20 to 60 for different values of the parameters. Now this is a full numerical simulation, a comparison between the asymptotic shown here and the solid line is effectively what you would get from the equation, the PDE, solving it here with spectral methods. Okay, this work with postdoc David Simpley and former postdoc Nikos Savas. So the agreement it is quite good. So it means you can actually analyze this model asymptotically. And now we're moving to some exploratory work to see what we can actually do with, let's say, simple Navier-Sleep model and, for example, chemical heterogeneities. This is work with PhD student Raj Veligiri. Here, these heterogeneities are effectively described by some function G, which denotes the local contact angle variations. Yes?
The previous one,
Yeah.
can you remind us what you prescribed and why it stopped where it stopped?
Where? Here.
Yeah.
We don't prescribe anything. It will just stop until this angle here reaches the equilibrium angle. Yes. So this is the asymptotic equilibrium for large times. Yeah. And this angle is effectively linked also to the conservation of mass to the system. Yes. So G, notice this heterogeneity function enters the equation through the boundary conditions. Okay. That's a comparison in the gray line between the asymptotics and the full line with the solid line, the numerics of the full PDE. Now we have two bumps in the heterogeneity, and you can see that the droplet is going to get stuck at the two bumps in heterogeneity. And we get also various other effects that we have explored, like stick slip and so on. Yes, we have actually analyzed all these effects in detail. What also we can do is the asymptotics here, a set of two ODEs. These parameters here, this phi here is effectively a macroscopic contact angle. This is effectively the slope of the leading order outer region right at the contact point. Yes. Although the numerics is not so difficult to do, the analysis is useful because you can actually explore various things, as I will show you, and hence why we do the analysis. But one other point here is hysteresis when a droplet spreads on the same substrate. Yes. So you see this hysteresis jump for the apparent contact angle. So although this is a simple model, you can still recover some of what people see experimentally, some of the phenomena. And of course, we can do also phase plane analysis for the two droplet radii A and B. You see here a constellation of fixed points shown here, stable nodes, saddle points, and stable nodes. Q1 and Q2 are, correspond to wetting enhancement, and Q3 corresponds to wetting inhibition. Inhibition and enhancement compared to the equilibrium to the spatially homogeneous case G equals 0. Okay, this is the spatially homogeneous case, this blue line. And this is another representation of the fixed points. These fixed points are effectively minima of this interfacial energy, minimum of this landscape, if you like, for the interfacial energy, as one might expect. Okay, this was suggested to us by a referee of this paper, who I'm not going to name. And moreover, what we can also see here is how the dynamics evolves, what happens to the droplet as you start, let's say, from an initial condition here. You end up to a stable fixed point here, and then you start somewhere here, and then you are going to end up to a minimum somewhere here. Now the green lines are the full PDE, and the solid lines are the asymptotics. Moreover, what you find is that localized defects are interesting in the following sense. If you, let's say, for example, prescribe the heterogeneity function, if this quantity here, epsilon, that measures the strength of the heterogeneity is sufficiently small, then the droplet does not fill effectively the heterogeneity. So the last time dynamics is what you would have in the spatially homogeneous case. And in this phase plane, L here is a measure of the droplet midpoint, D is a measure of the droplet radius. You can see that all initial conditions end up to this blue line, which is roughly square root of 3, which is the droplet equilibrium radius for the non-dimensionalization we have chosen. Increase the strength to 0.4, and suddenly you see a window here of width delta L, where a stable fixed point appears, and it means that initial conditions in this width, if you like, envelope, will end up at this point, which is different from the equilibrium. And then using continuation techniques, you can actually trace the width of the basin of attraction here, for which initial conditions get trapped. I should point out that in all the settings that we have done, and also for the topographical substrates we'll see later, we don't see Casey, Baxter, and we don't see Wenzel, because it's dynamics, okay? And Wenzel and Casey, Baxter are equilibrium, and in fact, you hardly ever see them in dynamics. Yeah? Okay. This is some exploratory work. I just wanted to show you that we have done, for example, work with phase field modeling. This is a very simple phase field model. This is the case of a meniscus in a chemically heterogeneous microchannel. So we wanted to see how the meniscus motion is affected by the disorder of these walls. So phi here is effectively a locally conserved field, okay, which displays the order of order parameter. It attains two limiting values, plus phi and minus phi, at the two faces. Mu is the chemical potential shown here. Alpha and beta are the two parameters that affect this potential V. It's a double well potential that has minima at the two values minus phi and plus phi. and these minima are given in terms of the parameters alpha and beta, so this is a quartic potential. Here is M is a mobility factor, and this is a one-sided model. And this is a wetting boundary condition due to Kant. W here is the width of the channel, and is unit normal to the walls, sigma surface tension, and A is a parameter which is proportional to the wall free energy. What's important here really is this average, if you like, value of the apparent contact angle as a function of the average velocity of the meniscus. And you can see here that you can quantify hysteresis for different values of the strength of the disorder. This is the standard deviation of a parameter which is also proportional to A. The chemical disorder here is taken as Gaussian white noise, okay? And you notice that as you increase the standard deviation, this hysteresis jump increases, and moreover, the jump scales linearly with the strength. And we have some physical arguments why this is the case. So this was work done with a visitor from Brussels. Mark Pradas, a postdoc in our group, drove largely the work. And recently, I mean last year, we had a paper in the Proceedings of the Royal Society with postdocs Marcus Smoot and Mark Pradas, our friend and collaborator in the Maths Department of ISC, where Darryl is, Greg Pavliotis, where we actually looked at rigorously upscaling using homogenization theory, phase field models, when this is strongly heterogeneous domains, so when we have strongly heterogeneous domains. Okay, let us move now to topographical substrates. I mean, substrates are never really smooth, okay, real substrates. These are in fact experiments, AFM microscopy experiments from Hitchcock and co-workers. These were done, were reported in A21, and they were done at Oxfordshire, the Harwell National Laboratory there, Materials Division. You can see as we move from something like alumina to vitreous carbon, we get an increasingly rough substrate. Eta naught here is an amplitude of this heterogeneity, and lambda gives you the range of wave numbers. So you have a higher range of wave numbers here. So we try to analyze this, and unlike the case with the chemical heterogeneities, now the topographical function eta with respect to some reference or datum plane, if you like, and there's both the equation and the boundary conditions. This was the Navier-Sleeve coefficient, and h becomes the deviation height with respect to eta. Okay. Now the primary difficulty that one faces with this system is the following. The requirement of substrate smoothness, together with the fact that noise is partial and enters the equations in if you like, in a nonlinear fashion, precludes from casting this problem into the, if you like, Langevin formalism of statistical mechanics. So with both Greg and Nico, we had to actually develop a specific, if you like, stochastic formalism to deal with this problem. And this was the first step, where we have a Fourier series with alpha m and beta m statistically independent Gaussian random variables. K naught is a characteristic wave number, okay, and n is the number of harmonics. Now this representation here is, it has sufficiently large Fourier content, especially as n tends to infinity, you approach Gaussian white noise, but you can also prove that it's sufficiently differentiable, so you can introduce it in the equation. Now later Nico extended this to arbitrary substrate spectral densities, yes? And it turns out that as far as the contact line statistics is concerned, the precise details of the spectral density are not necessary. You just need two what we call natural length scales. But in any event, what you can see here that these realizations that you get from this random representation are not so bad in terms, not so different in terms to what one sees in the experiments. I should have mentioned that these white lines are cuts of these FM images on the horizontal direction. Moreover, they give us a mild slope for the substrate, which is good from the point of view of the long wave approximation, unlike what one sees in the experiments. In the experiments, you would get, and this is in fact a misconception, because one might think that, well, the variation in the streamwise direction is much shorter compared to that in the vertical direction, but notice the scale at which these variations are reported. So in experiments, the substrate surfaces are reported in this compressed fashion. We can also obtain hysteresis, apparent contact angle, but now for the apparent contact angle we have to do averaging over several realizations. The black lines are the averages, okay, and these lines here are the green and the blue are effectively sample evolutions, okay. So still, although this is a simple model, you can recover some of these effects that people see in experiments. I think now we are in a position to start comparing the different models. Slip, precursor, Pisman and Pomont, diffuse interface as precursor film, not to forget the interface formation model. You can write all slip and disjoining pressure models in this generic form. Lambda is the slip coefficient, P is disjoining pressure. We have these three types of disjoining pressure. Van der Waals, sometimes M star and N star are taken as 3 and 6 respectively. Remember, this is the Sharma model. That's the Pisme-Poumon model. We view them again on the basis of this prototype. Yes, the droplet spreading, a generic inner region of order delta, some macro scale effects here, outer region without any of these effects. And here is the result. In the phase formation model here, we have already seen this rate of spreading equation. Let us talk about slip models. Slip models, interestingly, as I said before, the same rate of spreading equation, except this C naught is replaced by CNS. C naught here has to be determined from the inner region itself, as I told you, in a self-consistent fashion, although one can argue we still don't know the parameters of the problem, which affects C naught. But here CNS is determined when you fix the boundary condition at the contact point. If you take the static value, as is often done in the literature, CNS is 0. If you take this dynamic with some type of power load dependence, CNS is non-zero. Then we go to the precursor field models. There is some nice work by Pisman and Negus here. They looked at the Van der Waals model. We generalized this to an arbitrary disjoining pressure, and we had some other conclusions. Notice here the behavior of the inner region as you escape the contact line. It is affected by this length scale L, which satisfies this nasty expression. Luckily, we know this function K. This is the disjoining energy, if you like, the integral of the disjoining pressure, and different values of K for the different disjoining pressure models. Eventually, you get this rate of spreading equation, and if you set this equal to that, you can get an equivalence relation between slip and precursor field models. Now, this is something tricky here, because often people say, it doesn't matter if you use a slip or a precursor film, you get the same dynamics. We found yes, indeed. These equivalence relations persist even the quasi-static approximation, which is the underlying basis of these expansions, is violated. And this would be the case, let's say, if you have relatively fast dynamics, a droplet, let's say, on a vibrating substrate, is not quasi-static. But there are many other cases where these equivalence relations are violated, in particular when you have multiple droplet equilibria. And this is nothing else but a consequence of the different PDs that you're solving. After all, slip and precursor correspond to different PDs. So it is not necessarily true that it does not matter how you remove the discontinuity. And we published this work with Nico at this paper. And this is just to show you comparison between different models and just the effect of the bond number here. Bond number is effectively gravity over surface tension. And then what you can see is, as one might expect, it flattens the droplets. Okay? This is a very recent work with Nikos that appeared in JFM this year. Here we're looking at droplets on an inclined substrate. Okay? The reason why we got interested in these problems is because if you look at the spatially homogeneous inclined substrate, it turns out you do not have an equilibrium solution there because you have a third order OD that governs the film thickness, but you have too many boundary conditions to solve it. You have zero height, slope conditions at the back and forth, and also a conservation of mass. So it's an overdetermined problem. So we thought of introducing chemical and topographical heterogeneities to resolve this. Phi here is the inclination angle, alpha s is the static value. The solid line here is the full PD. These dots here is the asymptotics. That's the spatially homogeneous case. In the spatially homogeneous case, this is the speed of descent following an initial transient. Yes, we have a certain speed of descent. It becomes a traveling wave as a function here of, let's say, the bond number and inclination angle. Now, this is what happens in the spatially homogeneous case. The solid line is effectively the full PD, and the dashed line is the outer region. Okay, so we have a droplet sliding downstream here. Notice that for sufficiently large values of the inclination angle, so the inclination angle changes here, yeah, let's say 0, 10, 20, and so on degrees. At a sufficiently large value of the inclination angle, you get in a physical outer region because you cross the substrate. But in any case, this is what the droplet looks like when it slides.
Didn't you just say it's overdetermined?
Sorry? It's overdetermined, yes. So it slides.
So how did you get this plot then?
How did we get? We have an extra equation for the speed. I can tell you this later, yes. But if you put chemical and topographical heterogeneities, again we look at the phase plane here. Now these solid lines are the stable manifolds, I believe, and these dashed lines are the unstable ones. If the droplet starts from somewhere here, then effectively a long times you end up at about time 100 here, and the droplet is at equilibrium, so it stops, yes? And these are the different droplet shapes, where effectively you stop at for large times. Okay. Now this is some work we have done recently. We haven't published it yet because we're not sure about a few things. So this is a droplet climbing on an inclined substrate, okay, which is spatially homogeneous. There is some nice work here by Brune, Eggers, and Deegan, and Karen, John, and Uwe here. The droplet here is the substrate is vibrated with an angle psi, phi is the inclination angle. Angle psi is the angle between the axis normal to the substrate and the direction of vibration, yes, axis if you like. So what we see here is that for a spatially homogeneous substrate, we have these wild oscillations, this if you like swinging motion, but eventually on average the droplet seems to be climbing upstream, something that was explored in detail here by Karen, John, and Uwe Thiele. Now what is interesting here is that if you introduce topography, you more or less lose the swinging motion, and the droplet is much more determined. You have this kind of crawling, climbing determined motion without any swinging, and moreover you have this relaxation oscillations here. In addition, if you switch off for the same conditions, if you switch off the topography here, the droplet slides. So somehow the roughness actually helps the topography helps the droplet to climb. But as I was saying before, I mean, this is preliminary work, and hence we have not published it. Now this is Nikos' artistic efforts here. We presented first, I think, at the multi-flow meeting in Dresden. This is an analytical result, by the way, because if the droplet, the deviation of the droplet radius from a circle is not so large, you can solve this problem analytically. So we follow here the centroid of the droplet effectively, and what the droplet does is you start from a less hydrophilic substrate, somewhere here, and then it's following a trajectory towards a more hydrophilic substrate, and then it's going to get stuck at some point. In some sense, it follows a path of least resistance. Yes? And let's see it stopping somewhere. This is a chemical checkerboard pattern. Yes, that's a checkerboard pattern. And then notice also that any undulations at the beginning, because it's just capillarity here, there's no mechanism to destabilize the contact line. You look at this from the top, are actually wiped out by capillarity. Diffuse interface models. We did some work on diffuse interface models, and let's see what we did. So, so typically what one has is a free energy shown here. This is effectively a Helmholtz contribution. F bar, we have left it as a general function. It's a double well free energy term. This is a gradient energy coefficient taken to be constant, and G bar is the chemical potential, and this is a contribution from the wall free energy. Now, if you do a calculus of variation with respect to the fluid density, you set this equal to 0. And divergence theorem here, you get various terms. Some of these terms go to the wall. And then you get the equation for the chemical potential, and also a derivative of this function because you differentiate this integral. So this is the wall condition. The thickness is epsilon, okay? And in fact, you can obtain the surface tension by integrating the density in a direction normal to this interface. We take for the gas phase to have a zero velocity. In a previous contribution that was published, in fact, no, it was published recently, we took the viscosity of this phase also to vanish, and we had some other simplifications. And then what we have here for the governing equations is the continuity, compressible continuity. Stokes, that's why we have highlighted this with a lighter color, yes. Stokes equation, no slip, no penetration. This is the so-called capillary or Korteweg stress tensor, appropriate for diffuse interfaces, and this is the viscous compressible stress tensor. Mu is a viscosity, and nu is another viscosity. Non-dimensionalization here, typical scales on the problem. Okay, some length scales, some velocity, some viscosity. The main parameter is the K number, which is epsilon divided by this length scale. We also have the capillary number, the usual capillary number, and a modified quantity here. The two can be linked via this double well potential function. These are the dimensionless equations shown here, and in the squares, the equations, the simplified Stokes equation here, and the boundary condition, no slip, no penetration, and the wetting condition. That's an interesting condition because what we have done here effectively is we have taken a cubic for the wall free energy, okay, because a cubic is a good polynomial, Jimmy knows this. If you differentiate it, you get a quadratic, and the quadratic can be satisfied at rho equals 0 and 1, which are the two bulk values. Then this means that the grad of rho right on the wall vanishes, hence you exclude the possibility of any density gradients there, any boundary layers that could be used to, like a precursor film and so on, that could be used to remove the discontinuity. The idea here is if we can have a model, yes, without any macro scale effects at the contact line, and if we can see this, if this model can actually be used to remove the discontinuity. But first we have to recover the sharp interface limit. That is, we want to see if the classical formulation away from the wall is recovered, okay, in the sharp interface limit. We have to do this as a check. And for this we introduce these body fitted coordinates because the null is simplified. This is effectively an arc length coordinate, and this is a length from the interface. And then if we take the limit of, if we look at the limit of small K numbers, this is appropriate expansion here in powers of K number. The bulk outer region, yes, we recover the usual incompressible continuity and Navier-Stokes equations. In the interface region, the appropriate inner coordinate is here, zeta 2, okay? And then if you take this interface region towards the bulk and you match, you recover continuity equation, continuity velocities, this is the tangential and the normal stress balance. Moreover, if you specify the function f here, the double well function term, like we did recently in this paper, you get this hallmark of any diffuse interface method that you have a hyperbolic tangent dependence. So we recover the classical formulation away from the contact line. So this then justifies going back to Moffat, looking at the biharmonic equations for in each region, and there are some parameters that one has to fix. For example, here viscosity ratios and so on. But notice in these two cases, to the left the viscosity ratio is 0, so phase B has 0 viscosity. To the right, phase B has the same viscosity with phase A. Topologically, the streamlines in the vicinity of the contact line are similar. This is just to connect with the classical problem. We're not done yet because we have to look at the contact line region, and for that we introduce, as before, as the classical problem, a coordinate system in the vicinity of this line, okay? And if we consider the limit of 0 K numbers, this rescaling of the polar coordinate R gives us the following equations and also achieves dominant balance in these equations. Next, asymptotically, we look what happens as this new coordinate R tilde tends to 0. So we expand density and velocities in powers of R tilde, and then you can see the pressure and the stress components. So this now shows they're all order 1 parameters, and it shows that the contact line singularity has actually been regularized fully. Recall that the interface formation model has actually the following four results. Effective slip at the solid surface, okay. It does allow for dynamic contact angle variation. It does have the rolling motion, and it does have finite pressure of the contact line, okay. Remember the rolling motion only in the modern formulation when you include these mass transport effects between the bulk and the surface layers. The interface formation model, and here we summarize again what the interface formation model has. The diffuse interface model we have already seen has finite pressure. From the slide, recall Moffat, we saw the rolling motion there for the streamlines. But still one can strengthen this, and this is effectively boundary conditions that have been suggested in the literature by people like Jimmy Fegg and so on. For example, one might want to relax the dynamic contact angle variation. Here, if L bar is 0, we recover the wetting condition we had before. If you put now some type of relaxation timescale alpha in multiplying this term, then you can allow for a dynamic contact angle, for variation of the contact angle dynamically. For example, in a frame of reference, in a moving frame of reference where you are stationary, you lose this term, and then you get this expression, which can be then expanded for small contact angles, okay? So you can see that you have a dynamic contact angle, which is the static, plus a correction which has speed dependence. And this P here is a dimensionless parameter which involves this relaxation scale, time scale alpha. Or one might want to include slip, as shown here, for example. This is a shear stress on the wall, and this is a slip coefficient. Now, often Sepes's work is referred to when one says that the diffuse interface model removes the discontinuity. But in fact, if you look at the paper carefully, you will see that he discussed asymptotics, but he never really did the asymptotics. And also, he tried to probe the inner region numerically, but moreover, he had some constraints, for example, 90 degrees contact angles and viscosities and fluids of the same viscosity and so on. So we think ours is the first really analytical result which actually shows that the diffuse interface method can remove the discontinuity. A review of this diffuse interface methods is given in this annual review of fluid mechanics paper. Now, some authors, Kian, for example, and co-workers, they also include the sleep, yes, because they have done molecular dynamic simulations which indicate sleep, so they would like to model sleep. Others, like Fan and co-worker, also include sleep, okay? But you see, so one can say, okay, so here is a model where you have actually the discontinuities are removed, okay? And at the same time, you satisfy the no-sleep boundary condition, so why not remain with this model? The problem is, if you like, that the model is still phenomenological in the sense that you have this interfacial thickness epsilon that you do not know beforehand. In fact, epsilon is not the molecular scale. What the interface formation model is, or what the diffuse interface method is trying to do, is trying to approximate what is happening in reality. And in reality, if you have an interface, various quantities like, for example, densities, very rapidly but smoothly within a thickness of a few molecular diameters. The diffuse interface method does not have information from the molecular scale. In fact, epsilon has to be much larger than the molecular scale, okay, and also much smaller than the macro scale, because then this way we can achieve scale separation, if you like, and also one can justify the continuum equations which are the basis of the diffuse interface method, okay? So what one then does in a numerical setting, you have to try to set epsilon, to do a numerical convergence study, okay, to set epsilon to 0, to see if you recover the classical approximation, away at least from the wall, or do it asymptotically as we did here, but it's not always very easy. Is there anything else we can do? Before we do that, just to show you here the versatility of the diffuse interface model with the different, if you like, conditions. Here you have to fix the double well function and the viscosities. Okay, this, for example, slipper dynamic contact angle, and this is just a precursor film, that's the Pisman and Pomon model and so on, just to show you that it's versatile, as we said before, so you can modify the boundary conditions and so on. Okay, is there anything else we can do? There's something else, and perhaps, Len, did you talk about this? I wasn't here. Did you talk about this? I'm not so sure. Okay.
Well, I was talking.
Oh, you were talking. Oh, yeah, yes. So perhaps there is something, and it comes from the statistical mechanics of liquids community. And in some sense, if you like, it's rigorous, perhaps precisely because it can be obtained from first principles. But on the other hand, it also contains information from it retains some information from the macro scale. So this is a density functional theory, or DFT for short. Some rigorous results. A nice paper, review paper by Bob Evans and Tarazona here, subsequent paper. Another paper, as far as dynamic density functional theory is concerned, this is in fact in its infancy, by Andy Archer and Bob Evans. Archer is a lecturer in mathematics at Loughborough, so he's a colleague of Hoover's, and he has done some nice work here. We have then Rex and Logan, and ourselves, Ben Goddard, a postdoc in our group. With Ben, we have some rigorous results on dynamic DFT, which appeared in SciAM multi-scale modeling simulation last year. So the aim of this, if you like, is to try to understand well, first to understand contact line at equilibrium. There is some interesting computations for nanodrops by Bering and Rukenstein, and some interesting thoughts by Len Pisman on how to couple DFT to hydrodynamics. We feel they're not sufficiently rigorous, and we can discuss this if you like. So our aim is effectively to try to understand first influence on phase transitions and wetting properties, then move on to systematic derivation of a general dynamic density function theory to include hydrodynamic interactions and inertia, not in the usual hydrodynamic sense, but microscale inertia, yes? Without this, the particles would actually respond instantaneously to external stimuli, yes? So we have to have a finite friction coefficient for this to happen. To capture actual physical systems, we have to move progressively to more complex free energy formulations, and then eventually we want to see if we can measure macroscopic quantities such as contact angles. So this is current work and also future work. So first, equilibrium density functional theory. So I'm going to try to go through some basic elements of this from statistical mechanics. The formalism here is grand canonical ensemble. In thermodynamics, this means the system is open and particles can enter and exit as they please. And then there exists a functional known as a grand free energy functional, yes, which is minimum at equilibrium. Calculus of variations can be used to show that the necessary condition for that is this one. This is the variation of the fluid's free energy with respect to the density of the fluid. This is the density in the statistical mechanics sense, not in the macroscopic sense, because the particles are at finite distance from each other. So effectively, this one is sum of delta functions. That's the external potential. This is wall, if you like, and that's the chemical potential. Now, the fluid free energy, the way this is done, well, there are different ways, but this is one of the simplest ones. And what I'm showing here is a very simple formulation known as a low density approximation. You typically have a hard sphere reference repulsive fluid shown here, and then the attractive interactions are treated perturbatively. And this is the expression up to and first order terms in these attractive interactions. There is an equation of state that we have to use for the hard sphere part, and this is the Carnahan-Starling, okay? And that's the ideal gas contribution, and this term here contains eta, this is the packing fraction, and d is the hard sphere diameter. Beta here is an inverse absolute temperature, and Kb is Boltzmann constant. And then the prescription for the attractive part is effectively Lennard-Jones. That's the Barker and Henderson approach. More sophisticated ones exist also, yes, like Chandler, Wicks, and Anderson, and so on, yes? Marcus, yeah? Yeah, okay. So, but this here, epsilon is the strength of the potential, and sigma is some length scale. So this work that was done by former postdoc Antonio I mentioned earlier. Before we go to this contact line problem here, we need to first understand the film case. We need first to understand the case without any contact lines. This is what we're going to try to do here. In blue, we have the DFT equations. In red, we have something which is known as square gradient. You try to approximate this by expanding the density up to in terms of order 2 in the density, assuming that the density is small. So you convert the equations to something like this. So you go from a no local integral equation to differential equation. And you can relate this expression here to the gradient energy coefficient we had in a diffuse interface method earlier. All right, let us move now to this slide. In the absence of any wall, you have a very specific value of the potential, the chemical potential, which is known as saturation value, okay? And this specific value is such that if this chemical potential is larger than saturation, then you have the liquid is the preferred state, because then the grand free energy function has a minimum the liquid density. If the chemical potential is smaller than the saturation value, then you have the gas is the preferred state, because the free energy function has this, if you like, has a minimum this density. Now, what happens if you put a wall and mu is less than mu sat? Remember, mu less than mu sat means that in the unbounded case, no wall, you get the gas as a preferred phase. Here, mu is less than mu sat, and you have a wall. You see here the formation of a film in the immediate vicinity of the wall. So an attractive wall stabilizes a thin film in its immediate vicinity. That means that the only reason why this film is there is precisely because of the wall. Okay. Now, as mu tends to mu sat from below, this film thickness tends to infinity because you try to approach this case. So it's like the wall is not even there. Of course, the wall will be here, but it's like the wall is not even there. Notice also this undulation here. That's just LBA, but of course this can be proved with something like fundamental measure theory and so on. There is effectively absorption of particles in the immediate vicinity of the wall. And notice also that the square gradient and DFT give similar results. However, if you start looking at quantities like gamma, which is the absorption, if you like, that is a measure of this film thickness, effectively the integral of this profile from 0 to infinity. This is in units of molecular diameters, yeah? This is the hard sphere diameter, so here is 50 diameters. So gamma is an integral measure of this profile. You see now substantial difference, dramatic difference. You go from a single value curve to a multi-value one, okay? Which then, of course, has significant consequences for stability and so on. Now, what are the different parameters here? This is the location of the wall. The wall is at 0. This is the location of the wall fluid dividing interface. For simplicity, the two are the same. Sigma W is the strength of the wall potential, so we also treat the wall. This is the length scale of the wall potential. Epsilon W is the strength of the wall potential. And this is the critical temperature. So we are actually relatively far from the critical temperature. Yes, this is a mean field approach. something like the correlation length diverges as you approach the critical temperature. And then one has to use this interfacial Hamiltonian approach that our colleague Andy Parry, yes, from Imperial has been working on over the years. So we're sufficiently far from this critical point. Okay, so let us look now how this gamma disadsorption isotherm behaves as a function of the distance delta mu, which is mu minus mu sat, the distance from the saturation value of the chemical potential. If the wall is sufficiently, if the strength of the wall potential is sufficiently large, you see this monotonic behavior. But if you decrease the attractiveness of the wall, you make the wall weaker, you see that eventually you get this S-shaped behavior. Okay, so you have this S-type loop with a middle branch which is unstable and two lower branches. Okay.
Let's plot this the full DFT.
So this is the full DFT now for the adsorption as a function of the distance from the chemical potential.
So when you compare on the right side, you need to compare different parameters to see the same profile.
To see the same, yes, you would have to do this is in a different temperature here. So we'll look at the blue line here. So when you have this S loop, yes, curve, it turns out that there is a particular value of the chemical potential, and people in the statistical mechanics of liquids knew this. Okay, so we have an S-shaped loop. We have a particular value of the chemical potential. Let's call it coexistence, because we use saturation for where liquid and gas are at equilibrium. So we call this coexistence, where a thin film coexists with an equally stable thick film shown here. Okay, and this middle branch is unstable. So thin film coexists with an equally stable thick film. Well, the first thing that we had to do actually was to construct the interface shape, and this is a fully 2D computation, which is non-trivial, that connects a thin film to a thick film. And it turns out that the interface has some kind of pancake shape as you go from a thick film to a thin film. At this point, what we have is what is known as a pre-wetting transition, which is a first-order phase transition. If you then take this coexistence film from the left towards the saturation value, it turns out that this thick film here tends to infinity. So you have a situation where you have a thin film coexisting with an infinite thin film, and then the pancake gradually converges towards a wedge that we have seen before. Yes? So we have this well-defined liquid wedge with a well-defined nominal contact angle, and see that this wedge seems to persist sufficiently far from the wall. It's about 45 diameters, it's about 25 molecular diameters, and ultimately it will actually enter the macro scale. So we can use this now concept to connect the micro to the macro scale. Moreover, ahead of this wedge, we have always this nanoscale film, which is a few molecular diameters. We shouldn't be surprised because it's here. It's because the wall is attractive. In fact, the wall has two parts, an attractive part and a repulsive part. If you switch off attraction, you can't even make contact between the liquid and the solid. The attractive part is what stabilizes the thin film. So we cannot, I don't want to call it a precursor film, but we cannot get rid of it somehow. Now, what one can do is look at the topology of this area in some more detail. Okay, so notice that the interface is practically everywhere flat. These are the density level curves, except in the immediate vicinity of the wall, we get this undulation. This becomes much more refined by using something like FMT or the white bear approximation and so on. Notice also that as you make the wall less attractive, this apparent contact angle seems to increase, which makes sense. Yes. And the other thing that we can do here is, once we have the grand free energy functional, by subtracting from a reference bulk value and dividing by the area of the phase under consideration, obtain the surface tension. This is Young's equation written here in terms of the chemical potential. So we have written now Young's equation in terms of this formalism, and we can extract this angle theta numerical, we call it here, from this expression. And this is the measured one, geometrically measured value by extrapolating these flat interfaces towards the wall. And notice the agreement is quite good. Yes, there is a good agreement. So it means Young's equation and the geometrically measured agree. So again, this is quite encouraging. But as Jim Henderson from Leeds told us, Young's equation has also a normal component. So it's not good enough to just show that the tangential component agrees. You have to do the normal component as well, and that was highly non-trivial, took us much longer. Eventually it worked. Okay. The other point to point here is that if you go sufficiently far from the wall and you do a cut in the direction normal to the interface, this profile here is basically what you would get here. So you don't really feel the wall sufficiently far. Yeah. Now, this is some recent work we have been doing with PhD student Peter in the Journal of Chemical Physics and Physical Review he published. This is just to demonstrate that this is simple DFT, and what we do here, we trace the equilibrium states, yes, with respect to the distance from saturation, the chemical potential, yes. What to show you here, the confinement, now you go from a flat substrate, you close the system. It's a capped capillary, if you like, yes. To show the confinement, in a sense, acts as an additional thermodynamic variable via the Kelvin shift, if you like, yes, which is what? That the pressure drop across an interface affected by curvature and surface tension. And it affects the behavior of the system. It affects the behavior of the equilibrium. This is a pre-wetting transition, like this one here. In fact, I should have pointed out that these areas are in fact equal. And this is known Maxwell construction, yes, those of you who know about thermodynamics, if you remember Thomson's approach to thermodynamics and so on, yeah, with the metastable states. So, yeah.
Where is the water coming from?
Where? Which one?
The red, this.
Yes, so what you get here is effectively a drop. So you have a transition between a drop that starts here on this corner, and then, so the lower wall is actually hydrophilic, and the upper wall is hydrophobic. So we have a phase transition between the droplet on this corner here and this foot-like slab that actually extends from here to there. Okay, this asymmetry is because we have different characteristics, different wetting characteristics on the wall. And that is the corresponding bifurcation diagram for gamma as a function of the distance from the saturation. So there's condensation here. Yes, if you like.
The mass, where is it? This is 3D and you're looking at what happens.
No, this is 2D. That's a 2D computation, yes?
All this red mass, where does it come from?
From here. So you have the formation of a drop that grows. Yes? You have condensation of this vapor.
But that has low density and the red is high density, yes?
Yes, the red is high density, yes.
If you start blue and go red, this means there's a lot more mass.
But this is an infinite system, yes? This is an infinite capillary, yes? Yes, so you condense the drop. So the drop condenses at the corner and then it grows.
It's coming somehow from...
Yeah, it's coming from this. It's actually open. This is it's a semi-infinite capillary, if you like, yes. Yeah, so it's not finite, yes. Now, if you make the two walls equally, what you have here is a pre-wetting transition. This is the analog of the transition that we saw here between thick and thick film, but now due to confinement. Yes? So what you get here is these two droplets on the two corners. The characteristics of the two walls, the wetting characteristics, are equal. Here we're using a very simple dynamic DFT model. I'll come back to this in a second. And then now you have this liquid slab that fills the whole capillary. Now here, this is the bifurcation diagram for gamma as a function of this delta mu minus mu sat. This is the metastable curve, okay? And what we trace here with these field circles is dynamics. So this is what happens if you start from here. You just move up. Okay, gamma tends to infinity. But if you're very close, the initial condition is very close to this turning point. This effectively is spinodal. You slow down a lot. And in fact, if you start right here, you will end up at this point, and then you pin the system. Okay, so this is in some sense a glass transition, if you like, in generic sense, in the sense that you can actually freeze two droplets at the corner. So this is interesting from the point of view of actually trying to control this, the formation of the droplet. Yes?
What happens to temperature?
Temperature is fixed here. So we have fixed temperature here. All right, so however, this is, as I said, a very simple model, and quite recently we realized that in order to describe these systems accurately, remember I told you before about microscale inertia, in particular we need to take into account interactions between the particles themselves and particles and boundaries. So we had to enter into this field and try to derive a general dynamic density functional theory. So we had a series of articles here with our friend and collaborator, also Greg Pavliotis from the School of Mathematics, and postdoc Ben Coder, and the rest of our people. This is the most general DFT that we have come up as of yet. Yes, the rigorous results are here. Yes, there is an existence result in this paper here. So the red and the black terms do not have any hydrodynamic interactions. Okay, in fact, black correspond to inertia, and these terms here are highly non-trivial. These are non-local terms. For example, this term here couples with this term here, gamma is a friction coefficient, to effectively give some kind of density-dependent friction coefficient, and this one couples the velocities non-locally. Okay. We extended this theory. We had recently a publication in the Journal of Chemical Physics to multi-species systems to two different particles, if you like, large ones with blue and small ones with red. So the overdamped case is gamma tends to infinity. Okay, so there is no inertia here, and the solid lines, solid red lines are the particles 1 with inertia, blue solid lines particles 2 with inertia, dust red one overdamped case, and dust blue overdamped case. The difference between the overdamped and the solid lines, as you can see, is not so much. So inertia here, we've chosen the parameters, so inertia doesn't do much really. But except at the start, of course, because the system has to start. Now the crosses here and the circles, depending on the coloring, yes, indicate also stochastic simulation. So this is full Lange event simulation, just to show you that the theory agrees with stochastic simulations. But what is interesting is that eventually you start from some initial condition, and you see that the peaks at these distributions for the particles are different. So you get effectively some type of phase separation by which the red particles fill the space in the middle of this in the middle of the space available by the blue particles, especially because they're smaller, so they can fit in. Now, this is a very recent computation by Ben, and in fact, these results were published at the Journal of Physics Condensed Matter. They generated publicity because this is as general, as I said before, as possible. So what we do here, we start with about 500 particles, which are actually centered at a potential about 8 here. Okay, so we have a spherically symmetric potential, and we switch it off. This is a hard attractive wall. So what we are trying to see here, how these particles are going to move towards the wall, and just to illustrate how important it is to take the hydrodynamic interaction into account. So the mean radial position is with blue, okay, and no interactions are with red. And what you see here is effectively the mean radial position is always higher with interactions. It means that in some sense there is an inhibitory effect as you approach the wall. Yeah? So the fluid has to be pushed out. This is just a computation very recent by Andreas Nold, our PhD student, just to show you the concept, to demonstrate the concept I mentioned before, that if you start with an attractive wall, you have contact, yes, and then you have this precursor film, or we don't want to call it precursor film, but there is this nanoscale film here. But eventually, as you make the wall less attractive, the droplet, as you can see, contracts, and it starts, it would like to actually detach itself from the wall. I haven't done so badly in terms of time then. And the conclusions are self-evident. Now, if you want to discuss any of this, I'll be here until Friday. Some of these points are actually quite subtle, yes, and might evolve, yes, lengthy discussions. Thank you very much. Thank you.
Yeah, more questions? No?
We already had some, yes.
What is the typical size for you to do this DDFT simulation?
You mean in terms of...
Yeah, the size of the simulated system.
This, what I showed you there was about 500 particles. Yes.
So would it be worthwhile to just make comparison with molecular dynamics? It's not expensive.
It would be, yes, if we had... we have actually, yes, yes, that would be interesting to do. We have a molecular modeling group in our department. So the question is to find the right material so we can actually compare. Do you see what I mean? Yes. And to have accurate enough simulations. If there are such simulations.
Question about the earlier part of your talk. Before you introduced surface heterogeneity chemically, or
Yes.
you had a calculation before that. I think that used surface formation theory.
No, we call that was Yuli's model that he refers to as interface formation model. Yeah.
So anyway, so you had a thin film calculation that showed apparent angle heterogeneity. Sorry, hysteresis.
Hysteresis, yes.
How did that come about? What's the core? Well, the theory is smooth. How did that apparent result come from?
You mean for the case of the topographical
Yeah,
calculation?
No.
that was back.
Before that,
Yeah.
there's a smooth surface, right?
No, but for the smooth surface we cannot get hysteresis.
There's jiggly parts going.
They are all for the heterogeneous.
No, it was always for heterogeneous, yes.
Not with the wiggles, they are all for some sort of heterogeneity.
Yeah. We can check.
Yeah,
Yes.
that can be done offline. Any other questions?
I didn't get what is, let's call, the problem with the diffuse interface theory. You mentioned the length of the interface, which have to be small respect to the macro.
You don't know, and this is what the problem, if you like, is it a problem or is it not? It's phenomenological in the sense that you don't know this thickness beforehand. It's an arbitrary value. It has to be small. It has to be small, but it's not the molecular scale. Because the equations, the underlying equations are continuum. DFT, on the other hand, although the equations are continuum, is a microscopic theory. Diffuse interface method, diffuse interface is not macroscopic theory. The reaging, disjoining pressure, and so on is mesoscopic, not microscopic. Yes?
Any epsilon within whatever distance would do.
That's why I said you take epsilon to 0 in a numerical setting to achieve convergence, at least at the macro scale, and or the asymptotics. The problem is when I did the asymptotics close to the contact line for diffuse interface, we fix the capillary, the K number, which is small, and we fix epsilon, and we send the K number to 0. If we set epsilon also tending to 0, we then go back to the classical problem with a discontinuity. So there is something subtle there.
Well, in diffuse interface, if you literally solve the equation, you obtain the thickness. But this thickness is about molecular length, and so it can be really.
And then it cannot be. Yes, this is, I suppose, some criticism. But I mean, these models, of course, are used and so on. You see, in the simplest case, we still did not have the dynamic contact angle variation with a diffuse interface. You have to build it in. It does not come. It does not come from the model. The dynamic variation. This is something else to discuss. Yes.
Any other questions?
All right. Thank you, Laura. Thank you.